Right, so there's a tiny piece of quartz inside your watch that's vibrating exactly 32,768 times every single second. And if it slowed by even a fraction, your whole day would drift. That's number one, and honestly, it's wild. But before we get there, I want to show you 9 everyday mechanisms hiding in plain sight, counting down to the cleverest thing you own and never think about. Let's start with the zipper, because I genuinely thought this was magic as a kid. The slider you pull? Inside it there's a little Y-shaped wedge. Going up, it forces the teeth together at a precise angle so each tooth's hook drops into the hollow of the one opposite. Going down, the wedge splits them apart. That's it. Gideon Sunback perfected it in 1913, and a modern jacket zip can survive thousands of cycles. The clever bit nobody mentions, no single tooth holds anything, it's the whole chain sharing the load, which is exactly why one bent tooth ruins the lot. Speaking of small parts doing big jobs, the ballpoint. Before it, everyone used fountain pens that blotted and dried out. Laszlo Biro noticed newspaper ink dried fast, so he made an ink thick like honey, and to write with paste he needed a tiny rotating ball. Inside the tip sits a ball about 1 millimeter across, held in a socket with a few microns of clearance. As you write, it rolls, picking up ink from the reservoir and laying it down, sealing the ink from air behind it. That precision is why cheap pens still cost pennies but took decades to mass produce. Now, some pens click, and that click is a masterpiece. The retractable pen. Push the button, it clicks out. Push again, it retracts. There are no separate settings, it just knows. The secret is a rotating cam. Inside is a cylinder with angled teeth and a plunger that twists it a fraction each press. The barrel has vertical slots, deep ones and shallow ones. Each click rotates the cam so it either drops into a deep slot, locked out, or a shallow one, springing back. Parker's design used exactly this. I love it because it's a mechanical toggle switch, entirely analog, no electronics, running on one spring for years. Now from mechanical memory to keeping actual time. The pin tumbler lock. Inside is a plug that has to rotate, but 5 spring-loaded pins jam across it, blocking rotation. Each pin is cut into 2 pieces at a specific height. The right key lifts every pin so the cut lines up exactly with the shear line, the gap between plug and housing. All 5 aligned, the plug turns. Wrong key, 1 pin sits proud and it's blocked. Linus Yale Jr. patented this in the 1860s and we still use it everywhere. The reason lockpicking works? You can push pins one at a time, they don't all have to move together. Neat and slightly terrifying, from lifting pins to bending metal. Your old thermostat has no electronics. It runs on the fact that metals expand at different rates when heated. Bond 2 metals together, say brass and steel, into one strip, and when it warms the brass expands faster so the strip physically bends. Curl it into a coil, and that bend becomes rotation. Attach a mercury switch or contacts, and at your set temperature the metal literally curves enough to break the circuit and shut the heating off. It cools, straightens, reconnects. That's it, temperature control from a strip of metal that can't help but warp. This same bimetallic trick runs your kettle's cutoff. Now let's cook something with invisible waves. The microwave oven's heart is the magnetron, and it's genuinely brilliant. Inside is a ring of metal cavities around a central hot filament. Electrons boil off, but a powerful magnet forces them to spiral instead of flying straight. As they sweep past the cavities, they make them resonate, exactly like blowing across a bottle top makes a note. Those cavities ring at 245 GHz, and that's your microwave energy. It flings water molecules back and forth billions of times a second, and friction heats your food from the inside. Percy Spencer discovered it when a chocolate bar melted in his pocket in 1945. From spiraling electrons to a spinning ball. The old ball mouse. Before optical, you roll it, and a rubber ball inside presses against 2 little rollers set at 90 degrees, one for X, one for Y. Each roller spins a slotted wheel. On one side, an LED shines through the slots, and a sensor on the other side sees flickering light, flick, 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 as the slots pass. Count the flickers, you know how far and how fast. 2 axes, and your cursor moves. It's an entire motion tracking system built from a ball, 2 rollers and a strobing light. I still think it's more satisfying than a laser, right? Now the machine that keeps everything in sync. A camera's focal plane shutter is a race between 2 curtains. To take a photo, the first curtain drops, exposing the sensor. Then the second curtain chases it down and covers it back up. At fast speeds, say 1,000th of a second, the second curtain starts before the first even finishes, so what actually crosses the sensor is a thin moving slit. The whole frame is never fully open at once. That's why fast-moving objects can look skewed. The top of the frame is captured a hair before the bottom. Two flimsy blades moving in perfect sequence, thousands of times without fail. And now, the two I really wanted to show you. Before quartz, every clock's accuracy came down to one part, the escapement. A spring or weight wants to unwind all at once. The escapement rations it out in tiny, equal doses. An anchor-shaped lever rocks back and forth, and with each swing it releases one tooth of a gear, then catches the next. Tick, release, catch, tock. That's the ticking sound. It's the sound of time being counted out one